Hello and welcome to the channel. Today we begin our journey into graph theory, one of the most elegant and practical areas of discrete mathematics. Let's start with the fundamental definition. A graph G is defined as an ordered pair, written as G equals open parenthesis V, E close parenthesis. Here, V represents a non-empty set of vertices, also called nodes, and E represents a set of edges, which are either unordered or ordered pairs of vertices. Now, let's explore the different types of graphs you'll encounter. A simple graph has no loops or multiple edges between the same vertices. A multigraph allows multiple edges between the same pair of vertices. A directed graph, or digraph, has edges with direction, written as ordered pairs like open parenthesis U, V close parenthesis. A weighted graph assigns weights to edges, which we use in shortest path and minimum spanning tree algorithms. A complete graph K sub n connects every pair of vertices, while a null graph has no edges at all. Let me introduce some basic terminology. The degree of a vertex V, written as degree of V, is the number of edges incident on that vertex. A loop is an edge connecting a vertex to itself. Adjacent vertices are two vertices connected by an edge. A path is a sequence of distinct vertices connected by edges. A cycle is a path where the first and last vertices are the same. Finally, a connected graph is one where a path exists between every pair of vertices. Moving on to plane graphs, these are graphs that can be drawn in a plane without any of their edges crossing. This concept is crucial in circuit design and geographical mapping. For example, K sub 4, the complete graph on 4 vertices, is planar because we can draw all its connections without any edges crossing. However, K sub 5 and K sub 3, 3 are non-planar, which we can prove using Euler's formula and Kuratowski's theorem. Kuratowski's theorem gives us an elegant characterization. A graph is non-planar if and only if it contains a subgraph homeomorphic to K sub 5 or K sub 3, 3. This provides a concrete way to identify non-planar graphs. Now, let's examine Euler's formula, one of the most beautiful results in graph theory. For any connected planar graph, the relationship V minus E plus F equals 2 always holds, where V is the number of vertices, E is the number of edges, and F is the number of faces, including the outer region. Let me sketch the proof using mathematical induction on the number of edges. For our base case, consider a tree, which is a planar graph with no cycles. In a tree, E equals V minus 1, and there's exactly one face, the infinite region. Substituting into our formula, V minus open parenthesis V minus 1 close parenthesis plus 1 equals 2. This confirms our base case. For the inductive step, when we add an edge that forms a cycle, we create a new face. So E increases by 1, and F increases by 1. The expression V minus open parenthesis E plus 1 close parenthesis plus open parenthesis F plus 1 close parenthesis still equals V minus E plus F, so our formula remains valid. A practical application of Euler's formula is the inequality E is less than or equal to 3V minus 6 for planar graphs with V greater than or equal to 3. This inequality helps us check if a graph can be planar. Let's explore Eulerian paths and circuits, named after the great mathematician Leonhard Euler. An Eulerian path visits every edge exactly once, while an Eulerian circuit is a closed path that visits every edge exactly once. For undirected graphs, the conditions are beautifully simple. If all vertices have even degree, an Eulerian circuit exists. If exactly 2 vertices have odd degree, an Eulerian path exists but no Eulerian circuit. If more than 2 vertices have odd degree, neither an Eulerian path nor circuit exists. Let me illustrate with an example. Consider a graph with vertices A, B, C, D and edges AB, BC, CD, DA, and AC. The degrees are A equals 3, B equals 2, C equals 3, D equals 2. Since exactly 2 vertices have odd degree, an Eulerian path exists, but no Eulerian circuit is possible. Let's discuss Hamiltonian paths and circuits, which focus on vertices rather than edges. A Hamiltonian path visits every vertex exactly once, while a Hamiltonian circuit visits every vertex exactly once and returns to the starting vertex. The key distinction is that Eulerian concepts focus on edges, while Hamiltonian concepts focus on vertices. This makes Hamiltonian problems generally more difficult to solve. Dirac's theorem provides a sufficient condition. If G is a simple graph with n greater than or equal to 3 vertices, and the degree of every vertex V is at least n divided by 2, then G has a Hamiltonian circuit. Remember, this is sufficient but not necessary. Many Hamiltonian graphs don't satisfy Dirac's condition. As an example, K sub 4, the complete graph on 4 vertices, has both Hamiltonian paths and circuits. Any permutation of the vertices gives us a Hamiltonian path, and we can always return to the starting vertex to create a circuit. These concepts form the foundation of graph theory and have applications in network design, scheduling, and optimization problems. What is graph coloring? Graph coloring is the process of assigning colors to vertices of a graph such that no two adjacent vertices share the same color. Think of it as coloring a map where neighboring regions must have different colors. The chromatic number of a graph G, denoted chi of G, is the minimum number of colors required to color the vertices of the graph under this coloring condition. It's essentially asking, what's the smallest set of colors we need to properly color this entire graph? Why does this matter? Graph coloring has incredible real-world applications. In task scheduling, we ensure no overlapping tasks occur simultaneously. In register allocation for compilers, we optimize memory usage. In map coloring, we distinguish adjacent regions. And in conflict-free assignments, we avoid resource conflicts. Let me demonstrate with a simple example. Consider a triangle graph with vertices A, B, and C. The adjacent pairs are A and B, A and C, and B and C. Since this forms a triangle, each vertex needs a different color. So vertex A gets red, vertex B gets blue, and vertex C gets green. Therefore, chi of G equals 3. Now, let's examine some special cases that will help you quickly identify chromatic numbers. An empty graph E sub n needs only one color since no vertices are adjacent. A complete graph K sub n requires n colors because every vertex is adjacent to every other vertex. A bipartite graph always needs exactly 2 colors. For cycle graphs C sub n, you need 2 colors if n is even, and 3 colors if n is odd. There's also a practical approach called the greedy coloring algorithm. This simple heuristic processes vertices one by one, assigning each vertex the smallest color not used by its neighbors. While this doesn't always give the optimal coloring, it's very useful for approximation in real-world applications. Now let's explore one of the most elegant results in graph theory, the 5-color theorem. The statement is beautifully simple. Every plane graph can be colored using at most 5 colors such that no 2 adjacent vertices share the same color. Why focus on 5 colors when the famous 4-color theorem exists? The 4-color theorem, while true, requires a complex computer-assisted proof that's difficult to verify by hand. The 5-color theorem, however, has a clean, elegant inductive proof that we can understand completely, making it foundational in discrete mathematics education. Let me walk you through the proof outline. Our goal is to show that any plane graph can be colored with 5 colors using mathematical induction. For our base case, any plane graph with fewer than 6 vertices can obviously be 5-colored since we have more colors available than vertices. Our inductive hypothesis assumes that all planar graphs with fewer than n vertices can be 5-colored. For the inductive step, here's the key insight. In any planar graph, by Euler's formula, there must exist at least one vertex V with degree less than or equal to 5. This is a crucial property that follows from the structure of planar graphs. We remove this vertex V from the graph. The resulting graph G' has n-1 vertices, so by our inductive hypothesis, it can be 5-colored. When we add vertex v back, we have two scenarios. If v has fewer than 5 neighbors, we simply assign it a color not used by its neighbors. If v has exactly 5 neighbors and all 5 colors are used among them, we employ a technique called Kemp chains. This clever swapping technique rearranges colors in connected components to free up one color for vertex v. Let me illustrate this. Suppose we have a planar graph with vertex v of degree 5, connected to vertices a, b, c, d, and e. If all 5 neighbors use different colors, we use Kemp chain logic to find two connected vertices using the same two colors, then swap their color zones, freeing up one color for v. Hence, any planar graph G can be 5-colored, completing our proof. Finally, let's explore the practical applications that make graph coloring so valuable in solving real-world problems. In exam scheduling, students become vertices and shared courses create edges between them. If two students share a course, they are connected by an edge. The chromatic number tells us the minimum number of time slots needed so no student has conflicting exams. For map coloring, countries or regions are vertices, and shared borders create edges between adjacent regions. The chromatic number determines the minimum colors needed so no adjacent regions share the same color, ensuring clear visual distinction. In frequency assignment for wireless communications, cell towers are vertices, and potential interference creates edges between nearby towers. The chromatic number helps determine the minimum number of different frequencies needed to avoid interference problems. In task scheduling, individual tasks become vertices and dependencies create edges between them. If task A must be completed before task B, there's an edge between A and B. The chromatic number indicates the minimum number of time periods needed to complete all tasks without violating dependencies. These applications demonstrate that graph coloring isn't just abstract mathematics, it's a powerful tool for solving optimization problems across diverse fields. The beauty lies in how these simple coloring concepts translate into practical solutions for complex scheduling and assignment challenges. Remember, the key insight is that graph coloring transforms messy real-world problems into elegant mathematical questions about the minimum number of colors needed. This is the power of mathematical abstraction, converting practical problems into clean, solvable mathematical frameworks that we can analyze systematically. That's a wrap. Thank you for watching this video. Don't forget to give it a like, share with your friends and subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.